All right, today's the day where we are going to push through to the result about the metric connection. And the metric connection is a connection, so it's going to be expressed in connection coefficients. A lot of this will be done in a mix of the comp notation and the CFREE notation, so we'll be exercising all of those things. But we're looking for this connection on the manifold, or in the CFREE notation, this connection on the manifold that binds together the connection which is bound to the metric tensor. The metric tensor in CFREE notation is just G, and it's understood to be a tensor field. So we could write G of X, right, and it would still be in the CFREE notation, but usually we just write G because it's a tensor field. And in the comp notation, of course, it's G mu nu as a function of X, dx mu dx nu when we use the regular coordinate components, or the coordinate-based components of, or the coordinate basis of the vector spaces. And this is an element of the 0, 2 tensor product space. And all of these, as viewed as a machine, it's just a 0, 2 tensor. So as a machine, it would take two vectors, x and y. And this expression here, remember we have to understand that this is G as a function of space-time, takes two vectors, x and y. But of course, all of these x's have to be the same, right? Because you need two vectors at the point in space-time where the tensor, which of the tensor you've chosen. And this here is understood in the comp notation as G mu nu. I'll drop all the x's. Everything's a function of space-time, right? dx mu tensor product dx nu operating on x mu, or x, not mu, x alpha partial alpha, y beta partial beta, and ultimately the real number you get is just going to simply be G mu nu x mu y nu, right? And so this is a real number, of course, and that's exactly what we expect. That we expect this is a real number in the abstract sense. This is a literal real number if we actually plugged in the component values. So what we're going to ultimately show is how this object gives for us one of these guys. Now, this is not the presentation we're doing here. We're going to base it on everything we've done so far regarding the mathematics of the mathematics of the connection of the manifold. We're not going to make any physical arguments, right? But we're going to get the same answer you will get if you do make a physical argument. And maybe in the next lesson we'll do the more common physical argument. But we're doing a purely mathematical argument. You don't even need to lean on a lot of physics. But you do need to lean on a requirement. And you may remember we had this requirement for a parallel transport. We had this requirement that the dual space mapping under a parallel transport has to remain unchanged. And this is what we meant by that. And we're using this operator to just basically tell us the parallel, the vector, there's a vector field out there called, or a covector field out there called alpha. It has a value at s. We are going to parallel transport that along some specified curve omega from s to a new place t. So this is the parallel vector to alpha's value at s at t along the curve gamma, or along the curve omega, or whatever we name the curve. Actually, I think when we did it, we named the curve gamma, and then omega was just the operator. So we'll stick with that. We'll say the curve out there is gamma. And likewise, you can move a vector from S. The value of a vector field at one point, you can parallel transport it to another point, and you get the parallel vector there. And the not the inner product, but the dual space mapping of those two should equal the dual space mapping of the untransported vector and covector pair. So the trick that binds this all together, and maybe the thing that could be best interpreted in our context as our physical insight, is we want this to be true for the metric measurement as well. Which means if I take the metric of two vectors at one point in space-time, if I do a parallel transport of this thing, I should get the same kind of relationship, meaning, and the way I literally want that to mean, I'm going to write that down mathematically, is the following. If I take G at some point along the curve, remember parallel transport always involves a curve, and we're going to use gamma of tau, right? So if I take G and its value at gamma of tau, and I operate that on tau 0 x of 0 and tau 0 y of 0. I guess I got to erase this thing now. This line. Y of 0. What I'm saying here is I take a vector at the point tau equals 0, and I transport it to the point tau equals t. This should be a t. T. And that should be a t. These should all be t's. The curve is parameterized by y of tau. In this case, we're going to talk about gamma of 0 for these guys, and this is gamma of t for this one. So what I've done is I've parallel transported an x0 and a y0 from tau equals 0. I parallel transport that to tau equals t. And there I take the metric that's sitting there at gamma t, and I calculate the inner product of those two vectors. Notice I've got two vectors now because I'm dealing with an inner product. So instead of a vector and a covector, I have two vectors. So I calculate the inner product of these parallel transported guys. That should equal the inner product of G with the inverse transformation, T0 G gamma T, operating on X at 0 and Y at 0. Right? That's the rule that I'm going to enforce. So parallel transport does not affect the inner product. That's the idea. So with that fact in mind, what am I trying to say mathematically? Well, I've already stipulated it in one form, right? I've written, let me do it this way, G of some value tau, G, the metric tensor at some location where tau has a value of tau, of omega tau 0 x at the value tau equals 0, where I'll use this little subscript notation to start getting rid of all these crazy parentheses and gammas and stuff. We're going to tighten it up a little bit. Tau 0 of y of 0. So this is y at 0, moved to tau, parallel transported to tau, x at 0, parallel transported to tau, where g of tau is waiting for it, and I get an inner product. Well, that's going to be equal to the inverse of that, which is the transport from tau to 0 of g acting on x0 and y of 0. That's the mathematical statement of what we're interested in doing. And so we know, and this is true for, this has got to be true, by the way, for every curve, right? This has got to be true for any curve in space-time. This is just like parallel transport's inner products, right? This fact doesn't depend on the curve, right? the value ultimately, well, see the value of these two at one point, that's fixed. So it doesn't matter what curve and what parameter value you take, as long as it's parallel transport, you're going to get the same inner product, the same dual space mapping. And in this case, same is true. You're going to get the same inner product regardless of the curve and regardless of the parameter. So because of that, I can write that the derivative of this thing with respect to tau, the derivative with respect to tau, and I could calculate it when tau equals 0, of g of tau omega tau 0 x0 omega tau 0 y0, that has to equal 0, right? Because it doesn't change no matter what. So that's the whole point. That's the definition of the fact that it's constant along this, that this inner product is constant for parallel transported objects. So that expression is true. But now I'm going to explore this thing in here, right? And I know this rule right here. So I'm going to make that conversion. And I'll write d by d tau at tau equals 0 of omega inverse t0 of g tau x0 y0. That equals 0. But now I'm going to go in on my definition of the parallel transport of a tensor. This is a 2-2 rank tensor, and that's the inverse t0. We had a little bit of streamline notation before, where that would have been this thing before, but it's still the same idea. I just have the 0 in it, so I've added the 0. It's still the transport from 0 to s. That would be the transport from 0 to s, and then the inverse is from s to 0. So now we know, so we know what this is, and that's equal to the covariant derivative along the curve of g tau, which has to also equal 0. And that is a really, really important statement. You always see that statement in elementary general relativity textbooks, but I've never seen it really proven in a way that makes sense of it. This, to me, is much more of a logical way of getting there. But this basically is telling us that if you have a metric, the covariant derivative of a metric along any curve, along the tangent of any curve, has to equal 0. And another way of saying that is just the covariant derivative of g equals 0 everywhere. If that has to be the case, if, remember that this isn't always true. It's only true if we demand this to be true, right? If we demand this to be true, which is that the covariant, the inner product of parallel transported vectors does not change. And if we demand that to be true, then this is the implication. The covariant derivative of that tensor has to equal 0 everywhere. Which, of course, in comp notation is just g mu nu double bar delta equals 0. Which, if you really want to write the whole thing out, well, we won't bother right now. But that is the implication of our demand. So with that in hand, we start exploiting this to make our calculation. We'll begin by calculating the covariant derivative in the direction x of g applied to, and my notes have y and z in it, so we'll use y and z. And we know from our last lesson that in the abstract notation, this is x applied to the function y, z. Now, minus g applied to covariant derivative of y, z minus g y covariant derivative in direction x of z. Right? That was our basic definition from that's what we derived in our last class, except now we're using just a 0-2 tensor. And so both of these terms are vectors, right? These are both vector terms. Now this is a differential operator acting on a function. When G gives a real number when fed two vectors, so G is a tensor field when fed two vector fields gives you a function on the manifold, so you can take a differential operator and apply it to a function on a manifold. This likewise, and that result will be a function on the manifold. This, of course, is G given a vector, which is a function on the manifold. This is G given a vector, which is a function on the manifold. You got to remember, of course, that the covariant derivative of y in the direction of x is a vector. The plain old covariant derivative of y would be a 1-1 tensor, but we got that x there, which eliminates that covariant index and gives us just a contravariant index left over. So this guy here is a straight up function on the manifold, and that makes sense, right? Because this is a function on the manifold, and you know that the covariant derivative in the vector direction of x of a function on the manifold is just going to be another function on the manifold. So with that in mind, we have a new piece of information, which is that this is 0, right? So that whole thing has to equal 0, which tells us this. The differential operator x acting on G being fed y and z equals G being fed the covariant derivative in the direction of x of y and z plus G being fed y and the covariant derivative in the direction x of z. This is called the Ricci identity. And I got to admit, I don't know how to pronounce that. I think of it as Ricci, but it could be Ricci. Hold on, let me see if I can figure that out. Okay, I've been told it's probably the Ricci identity. I'm presuming it's Italian. That is, normally that would not be true, right? This is not true for all 1-1 tensors. It's only true for the metric tensor because of this demand. Because of this demand, this becomes suddenly true. And now we need to introduce something of an assumption. This is an assumption that's core to the theory of general relativity. And the assumption, I'm going to put it in red, looks like this. The assumption is that the covariant derivative in the direction x of a vector y minus the covariant derivative of a vector x. Oops, the covariant derivative of y in the direction of x minus the covariant derivative of x in the direction y minus the commutator between x and y equals 0. This is a very important assumption. Assumption of GR. It's an assumption of the theory of general relativity. Let's have a little bit of a look at what this assumption entails, and then we'll come back and finish our derivation. Okay, so this is the object we're going to break down, and we're going to in order to see how it actually looks, we're just going to go into the full comp notation here. The first thing we have to do is understand what this thing is. And in the CFREE notation, this literally would look like xy minus yx, which is always to be understood as x acting on y being fed a function minus y acting on x being fed the same function, right? And what this is x is a vector field understood to be a differential operator, so it can act on a function, and that will return another function, which can be fed to y. So it's the second derivative. It's called the Lie derivative. And likewise here, we feed the function f to y, and then come back with a new function, y acting on f, and then feed that function to x. And that's what this thing is. And so if we kind of broke this down into true comp notation, it would look like x mu partial mu y nu minus y nu partial nu x mu, like that. That's what that thing would look like. So, and then of course we know what this looks like. We know what this looks like and what this looks like. So let's write those down. This is going to be x, let's see, sigma times y alpha sigma plus gamma alpha sigma beta y beta minus y delta times x, well, let's do x alpha delta plus gamma alpha delta and rho x rho, right? So we have that, and then it's going to be, we're going to subtract these two from it. So then we have minus x mu gamma mu y nu plus y nu partial nu, I keep saying gamma when I mean partial sometimes, x mu. Alright, so this whole thing equals 0. And now notice I've gone to the full comp notation. I'm not using any basis vectors here, right? If I did, I guess there would be a basis vector here, alpha, and then here there would be a basis vector alpha, and then here there would be a basis vector nu, and here there would be a basis vector mu, I suppose. Okay, but I'm not including those things. But they are all vectors in that context. So with that in mind, we now look at these things, and we look at this term. This guy here is actually, I better do it in red. This guy is x mu y nu partial mu, right? That's what that term is, and this is y nu x mu slash nu, right? That's just notation. This here is equal to that, and this here is equal to that. So the point is this term here and this term here are the same, and they cancel because they have opposite signs. We're not looking at this anymore. We're now looking at this. Likewise, this term cancels with that term. And so all we're left with are these terms. And we can write those down, and I'll do it in green. 0 equals gamma alpha beta sigma y beta minus gamma alpha rho delta x rho. Oops, and then this one has a x sigma, and this one has a, I'll put on the backside, y delta, right? And that equals 0. Now, this should be true for, well, now we just have to juggle the indices around. I want the x and y superscripts to be the same. So I have to change, in this term, I would have to change rho to sigma and delta to beta, which isn't hard. So I will have alpha can stay the same, but rho becomes sigma. So I get x sigma, and delta becomes rho becomes sigma, delta becomes beta. Y beta equals 0, right? So now all I've done is renamed the indices on that right side. And then I look at this and I say, well, this is always true for any vectors x and y, right? Because if I'm saying this is true all the time, any x and any y will do, and it's still true. It's true always. So it's not true for a certain x and a certain y, or it's true for every x and y. So because of that, and I can now write this as x sigma y beta gamma alpha beta sigma minus gamma alpha sigma beta equals 0, but it's true for all x and y, therefore this must be equal to 0. And that ultimate result is the important one. Sigma alpha beta, gamma alpha beta sigma equals gamma alpha sigma beta. Phew. So what we're saying is this requirement here, that requirement here in CFREE notation is tantamount to this requirement in the comp notation, right? So this is now in the comp notation. Because if I literally translate this into the comp notation, by the time I'm all done, I end up with just this. And what this is saying is that the connection has to be symmetric on the lower two indices. So this whole assumption that I just said we got to make, that general relativity really leans on, boils down to the symmetry of the connection in these two indices. Okay, so now with that in mind, we can go back to our derivation. So remember this expression. Now what I'm going to do is I'm going to solve for this, and I'm going to solve it by writing the covariant derivative in the direction x of y is the covariant derivative in the direction y of x plus this commutator, or I keep calling it a commutator because that's like the quantum mechanics term, but it's the Lie bracket of x and y. And I substitute that up here, right? And when I do that, I now can write x, g acting on y and z equals g acting on x, z plus g acting on x, y, z. Remember, the Lie bracket, that's a vector, right? We showed somewhere. Where did I show it? I'm not sure where I showed it. But this Lie bracket is a vector. I did show it, didn't I? Yeah, that's right. I showed it right here. Remember, this guy here ends up being a vector, right? So you got to understand that. If you should work through this to see that that thing is a vector. So, and the reason that's important, of course, is because we're going to feed it to the metric, right? Which we can. It's not a problem feeding that to the metric. And then this thing plus g, y, covariant derivative in the direction of x of z. So that is the expression we get for that substitution. Now we can accelerate our work. I can obviously substitute here as well. But the point is for any vectors x, y, this is true. And this expression will be true for any vectors x, y, and z. So I can write this down 3 different times. I can write down y of g, z, and x equals g partial derivative in the direction z of y of x plus g y z x plus g z partial derivative in the direction of y of x. Right? That's just a simple rearrangement of the letters in a it's a correct rearrangement, right? I mean, I'm sticking with well, let's see. X becomes y, y becomes z, z becomes x. So if I start with x, y, and z, x becomes y, y becomes z, z becomes x. So that is simply a cyclic rearrangement. And we can do another cyclic rearrangement of this, right? We can then write z of g, x, and y is g, x, z of y plus g, and this will be z, x on y plus g, x partial z of y, like that. So I can write these three things down separately. And they're all three true. And understand, this is all by exploiting, it's very heavily leaning on this zero torsion assumption of GR, right? I made that zero torsion assumption. This is true for each of these versions, and then I just make the appropriate substitutions, and I get these three statements, which are mathematically equivalent, right? But I can now add and subtract these guys together, and I'm going to actually literally, I'm going to create this combination. I'm going to create the following combination. I'm going to do y, and this is very clever. I mean, it's not an obvious thing to do, but the guy who figured this out, a guy named Kozul, he's the one who generated this formula. Y of z of g x y minus x of g y z. I'm going to make that arrangement. So I'm going to basically take these three expressions and I'm going to create this linear combination. Y plus the z1, so this one plus that one minus the first one. And when I do that, we end up with the following 9 terms. So I'm going to write them all down. So when you do that, you end up with these terms. I just wrote them out off stream. And you can see these guys here come in from this term, the negative term, and then this and this are just literally replaced right here and here. And so now we start looking at this, and we remember a couple things. First, that the metric tensor is symmetric, right? It's symmetric in any space-time manifold. So some of these terms are actually equal. So I can look at partial yx of z, right? And I look for the other term that's got, I say partial yx of z, covariant derivative yx. Can I find another one? Here it is. And it's got a z here. So this term and that term are actually the same. And so they will cancel because of the negative sign. Likewise, xy and z, that's not going to go anywhere. But this last term, covariant derivative xz, covariant derivative xzy, so that term and that term will cancel. Right, so those two go away. And then I should see a few other things going on, right? Let's see. This term here and that term here combine, right? So I should get just a factor of 2 times that term. And then I've got these 3 guys left. So I can combine these two. So what I'll do is I'll cross that out and I'll put a factor of 2 in front of that one. And then I think that's all I can do, right? I think everything that's left I have to kind of work with. So what will be left? Let's write it out. So this is what it looks like. That's what this linear combination equals this after we've done all our cancellations and combinations that are left. Now, one of the last steps is you solve for this guy. And why are we interested in solving for this guy? Well, that we can calculate. If we know y, z, and x, we can calculate that. That's easy to calculate. If we know z, y, z, x, and y, we can calculate that. We can calculate that. We can calculate this, this, this. We can take the appropriate derivatives to calculate these as differential operators operating on functions. We can calculate everything. The one thing we don't, so everything, let's put it this way, we can calculate everything. We can actually calculate this too. Okay, so we can calculate everything. The point is that the connection is now isolated into this one term, right? That's where the connection lies. So if we can put this on one side of the equation and everything else on the other side, we have a fighting chance of solving for the connection, right? So let's do that. All right, and when we do that, we end up with this expression here. So the covariant derivative, the only covariant derivative is on the right-hand side, so we know when we expand that, we're somehow going to get the connection. And all of this is a bunch of stuff we can calculate. That means, when I say we can calculate, what I mean, in the abstract, what I mean is G eats two vectors and gives us a real number, then it's being a function on space-time, we can, this in x is a differential operator, we can then take a differential operator and apply it to that function on space-time. So I guess I should say a tensor field taking two vector fields gives us a function on the manifold, and I can take that I can take that differential operator x and act on that function. Likewise for those two. This, I can calculate that vector field, right? I've already shown that that's a vector, so if y and z are vector fields, that's going to be a vector field. X will be a vector field, and then the same rule applies. I can just calculate the inner product of that, and that'll also be a function on the spacetime. So everything over here is going to be some function on the spacetime. Likewise, that'll be a vector field, that'll be a vector field. When I calculate this vector field, however, the connection coefficients are going to come out when I make the conversion into the comp notation. So this here is called the Kozul formula. That is, this here is called the Kozul formula. And it's in CFREE notation. So now to take that guy and convert it to the comp notation, and then finally we'll get that expression that we saw in the catalog, right? So there's the Kozul formula. Put it down there. And so now we have to remember, so what does it mean to convert this into the comp notation? Well, it means we're looking for the components of everything. And in order to have components, we have to establish a basis. But the basic idea is that we make the simple substitution. We're going to say x is the single basis vector E delta. Y is going to be the single basis vector, make sure I got this right. Z is going to, I'm sorry, let's do this right away. X is going to be the single basis vector, to keep consistent with my notes here, E mu. Y will be the single basis vector E nu, and Z will be the single basis vector E delta. Right, so now I can rewrite this expression as 2g partial derivative, Z will be E delta. We make that, see, this is subscripted subscripts, right? E delta, E nu, E mu. That's the entire left-hand side. And then this thing equals minus E mu, G E nu E delta, plus Y G, oops, Y. See, this whole point is not to write Y. E nu G E delta E mu. And let's see if I can squeeze the last one in here. Plus E delta G E mu E nu. Now these last three here with the commutators, right? We're going to be using the we're going to be using the coordinate basis, right? And in the coordinate basis, I partial j, those all equal 0 in the coordinate basis. The way I've written it in this sort of general basis with these e's, that's a little bit more just for just a change up of notation, but we are going to be doing this in the coordinate basis in the end. So all the commutators vanish, so this whole last line will go away. And then we now are in a position to make essentially our substitutions. We can start examining the first term, G E delta E nu E mu. Well, we know what that is. That's G, and this is going to be gamma nu delta alpha partial alpha. Let me make sure I'm consistent with my own notations. Actually, I used sigma partial sigma in my own notation. E mu, right? And then that is equal to gamma sigma nu delta times G partial sigma partial mu, right? And that, now we've fully switched into the coordinate basis. I guess maybe I should just put this up. Partial mu, partial nu, partial delta. And that will be gamma sigma nu delta G sigma mu, right? Because that's the definition, right, of G sigma mu, right? G sigma mu literally equals the, in the abstract notation, it's the tensor with the coordinate basis thrown down, or the two basis vectors. You feed it two basis vectors, you get its component in that basis, right? And that's what this is. So this expression here equals that guy right there. Now, what about the other terms? Well, the other terms, let's take a look at minus, oops, do it in red, minus E mu G E nu E delta. Well, those basis vectors in the coordinate basis is going to be minus partial mu G partial nu partial delta, which is minus the partial with respect to x mu of G nu delta, which we always write as G, which will be minus G nu delta single bar mu. And likewise for all these other terms. The other terms will end up being minus G delta mu partial nu, and then that's what this term will be. And then this last term will be minus G mu nu partial delta, like that. And so we can put all this stuff together, right? We substitute these three for these three, and we substitute this for this. And what do we get? We get 2 gamma sigma nu delta G sigma mu equals minus, oh wait, one of these has a plus sign though, right? Yeah, the first one has a minus sign, the other two have plus signs. So that's a plus and a plus there. So why don't we put the plus guys first? That's a plus and a plus. You just put the plus guys first, and we'll get G delta mu nu plus G mu nu delta minus G nu delta mu. So we have that, which I will just get rid of the 1/2, and I will put that 1/2 right here. And let's move this away a little bit to make it a little bit clearer. So this is so close to what we want, right? What we're looking for is the connection coefficient alone on this side here. Now, the connection coefficient is not a tensor, so the idea of using this as a lowering operator on that is really not technically correct. It's not a tensor process, right? It's not a tensor process. So what we can do is we can redefine this whole side as a new symbol, something we're not looking for, but a different symbol. Pretending, and we'll give that symbol, we'll treat that symbol kind of like a tensor, just for our comfort, but it's not really a tensor. We've just redefined that symbol, and G mu nu delta minus G nu delta mu. And voila, we've got the definition of something that's not what we were looking for, right? Because we were looking for the definition of this guy in terms of the metric. Instead, we've said, well, we didn't fully separate the metric, so let's just rename this whole side this thing and say we've accomplished something. And fair enough, right? That is called these guys are actually called the Christoffel symbols of the first kind, right? These will be the first kind. But fortunately, we do know that G sigma mu times G mu, where am I? G mu kappa is going to be delta kappa sigma, right? Where actually it's going to be. So with that in mind, I can multiply both sides by G mu kappa, and then I can multiply both sides of this guy by G mu kappa, and then I get T sigma nu delta, and then this will be sigma kappa equals 1/2 G mu kappa times G delta mu nu, one derivative nu, G mu nu, one derivative delta minus G nu delta, one derivative mu. And this delta symbol changes the sigma to a kappa. So I'll just erase that, and I'll erase that, and I'll put a kappa here, and then I'll check. We're left over with a kappa. That mu sums over everything, so there's only a kappa up there. Then I have a new delta on the bottom, so that'll be there's a delta and a new, a delta and a new, a delta and a new, kappa up there, mu sums away, delta nu left on the bottom, right? So that, ultimately, if I haven't made any screw-ups, is our answer. Phew. So that, the sum of about 5 or 6 different lectures here, but ultimately this is the connection coefficients in terms of just the metric tensor. And notice the first derivatives of the metric tensor are all in there. So let's compare our answer with the catalog of spacetimes. Yeah, I'm just trying to capture. So what we'll do is we'll take our answer and we'll go to the catalog of spacetimes and we'll see if it's the same. Hold on. There's the catalog of spacetimes. Gotta move. There's our answer. Okay, so they actually have, I guess we're going after this guy right here, right? We're going to compare that. So they have, for them, they have T mu nu lambda equals, and they have 1/2 G mu rho. So we have kappa. So yeah, so it's going to be tough to compare, but we got to do it. We got to do it. And then they have G rho nu lambda, G rho nu comma lambda. They use commas. And then they have G rho lambda nu, G rho lambda comma nu. And then they have minus G nu lambda rho, minus G nu lambda rho. Okay, so let's see if these things jive, or can be made to jive just by renaming things. So it looks like the correspondence would be kappa goes to mu. So we would have to go kappa mu 1/2 G mu G delta, oops, I don't want to, G kappa goes to mu. Where's our kappas? Oh, that's it. That's only those, that one. Okay, then our nus are actually in the same position. So this is a new plus G new bar minus G new space bar. That's good. So that puts the new there. Then our deltas become lambdas. So our deltas become lambdas. So the first one is is lambda, and the second one is our deltas become lambda. So that goes to be a lambda, and this becomes a lambda. And then our mu's must become rows, right? So our mu becomes a row, lambda row, G row, row. Okay, so we're only allowed to differ by an interchange of symmetric coordinates on the matrix. These are all symmetric in these indices, so we're only allowed to differ by that symmetry. So we have rho mu, they have mu rho. We have lambda rho, they have rho lambda with a plus sign. We have rho nu, they have rho nu with a plus sign. And we have nu lambda, and they have nu lambda. So those agree. So everything agrees. So I declare this to agree. And if I'm wrong somewhere, then you find it and dig it up. Let me know. But the only variance between this and this is the symmetry of G, and G is symmetric. And we used that symmetry earlier, so it's forced to be symmetric because we used that symmetry when we canceled out, and we ignored. Where did we do it? When we ignored. Hold on. We actually ignored something somewhere. We ignored those commutating terms, right? Yeah, these terms here. When we ignored those terms there, that was when we established the symmetry. So that's it. So we have now demonstrated this and this. And likewise, this, we had done that one too, right? That was, and you can yourself show the equivalence of this. That's this other alternative definition, the symbols of the first kind. So what that basically tells us is the way we've defined those symbols, the way we've defined these symbols here, you can actually raise and lower, but notice how it's done. They put the mu at the end, so to lower it, they put the mu at the end, and here's the relationship. They're raising that row to mu, but they put it up top here. So just keep track of that notation. And the notations do vary. Like I already showed you, the Straumann notation would turn everything backwards again. So there we have it. There you have the mathematical demand, in summary, the mathematical demand that the metric does not change, that parallel transport does not change the value of the inner product. Whether you parallel transport the vectors to a new point and then take the metric, then take the inner product there through the metric, or whether you shift the metric from a point to a point, if you parallel transport the metric to the new point, you still get the same value. This told us that the covariant derivative of the metric under such a circumstance would have to be 0 everywhere. And then from that, we proceeded to calculate the covariant derivative of the metric. And then we used this all critical and super important assumption of GR that this is true. And we'll talk about that more later. But without that, this whole thing falls apart. The answer does not work out well. It still works out, and people have worked it out, and we may work it out ourselves later on, just to show, as demonstration of what's going on. But then we go through all of this, and we end up with the Kozul formula. And then all we do is take the Kozul formula, which is in CFREE notation, and we spend all this time, all this time converting it into the comp notation. And when you do that, you land here, which takes us to the catalog of spacetimes, the Christoffel symbol of the second kind. So now we've mastered this, we've mastered this, that is a definition. This relation is just an obvious consequence of this definition, so that's, I'll call that mastered. And now it is time to move on to the Riemann tensor. And the missing one here is called the torsion tensor. And the reason it's missing in the catalog of spacetimes is the torsion tensor is always 0 in general relativity. But we're going to have to spend a little time talking about it. And then there's also tensors on the other pages beyond this, including the Weil tensor, which is very important. Okay, well, we've made it to this far, and we'll just keep pressing on to the rest of this catalog, starting with this in our next lesson.